In video 82 of Tensor Calculus, we'll introduce the Riemann Christoffel Tensor. This object, more commonly referred to as simply the Riemann Tensor, is the primary object we use to quantify manifold curvature from an intrinsic perspective. We've run across this expression several times in previous videos. We said that the covariant derivative is an operation that commutes for flat manifolds but not for curved manifolds. Well, in this video, we're going to expand this expression out and show that it leads to an object we can use to help quantify the curvature of our manifold. Now, let's remind ourselves of what we have here. This is an operator. It's not a tensor. It's an operation that is performed on this object that will produce a tensor, but it's not a tensor itself. Now, just as a side note, I've introduced an alternate form of the syntax over here. This is a little more concise, but it means exactly the same thing. So let's review what the exact meaning of this is. It expands out to this. Both of these operators expand out to an operation that starts with the covariant derivative with respect to beta. Then when we get that result, we apply the covariant derivative with respect to alpha. Then we repeat the operation in the opposite order, and the final result is just the difference of these two operations. So that's what we'll do to expand out the expression fully. The first step is going to be the covariant derivative with respect to beta of t lambda. Now by now this sort of thing should be second nature for you. We always start with a partial derivative. So the partial of t lambda with respect to s beta. And because we have an upper index, we need a positive term, and that's going to be gamma. Free indexes are lambda and beta. And we'll need a dummy index to complete this contraction. And there's the end result. Okay, now when we take a covariant derivative of an object, we always add another free index. So we started with a first-rank tensor here, but taking the covariant derivative now creates a second-rank tensor. So to make it easier to see where we're going here, let's equate this to the expression u lambda beta. We'll define u lambda beta as this expression right here to emphasize the fact that this operation creates a second-rank tensor. All right, so we've done this. Now we need to follow through with this operation. And that means we're looking for the covariant derivative with respect to alpha of the covariant derivative with respect to beta of t lambda. But because of our definition here, that's the same thing as simply taking the covariant derivative with respect to alpha of this new object, u lambda beta. Okay, so again, we follow up with the standard rules of finding the covariant derivative. Always starts with a partial derivative, like this time with respect to s alpha. And now I've got two indexes, so I need two terms here. First will be positive with the upper index, so we'll have gamma. The free indexes are lambda and alpha. We'll have our u term here. Beta is unchanged, but I need a dummy index here, and I'll use sigma this time. All right, now I need a second term. This time it's negative because beta is in the lower position. And we'll have gamma. This time our free indexes are alpha and beta. We'll have our object u, and lambda is unchanged, and our dummy index is here and here. And that's the result that we're looking for here. All right, well, the next thing we want to do is to eliminate these u components here by making reference to the full definition back there. So to eliminate this guy, I've got to take the partial derivative of this expression with respect to s alpha. So that means that we first of all take the partial derivative of the first term, and that's going to give us a second derivative of t lambda with respect first of all to s beta and then S alpha. All right, now I take the partial derivative of the second term, and of course to do that we need the product rule. So we're going to have the partial derivative of gamma lambda beta omega with respect to S alpha times our remaining term of T omega. And then I have the last term, which is gamma lambda beta omega times the partial of T omega with respect to S alpha. Okay, so you can see that this expression right here has now been equated to all three of these terms by simply taking the partial derivative of this expression with respect to S alpha. Okay, now moving on to this term, there's no differentiation here. I've just got to distribute this factor into each of these two terms. So we'll eliminate this by taking this factor and distributing it to these two. However, notice that our factor here is u sigma beta and not u lambda beta. So as we do this, we have to replace the index lambda here with sigma. So it's going to look like this. We'll have a plus gamma lambda alpha sigma, that's this term, and we'll distribute that first to this one, replacing lambda here with sigma. So this is the partial of T sigma with respect to S beta. And then we'll distribute it to this last term, which is going to be gamma lambda alpha sigma, distributed to this, again replacing lambda with sigma. So this is gamma sigma beta omega T omega. And finally, for this term here, we go through the same drill, only this time we have a negative sign, so we distribute the negative factor here to each of these terms, this time being careful to replace the index beta with sigma. So what we have now is this, which of course is this full operation, and we need to follow through now and do this one. Well, we could go through the same exercise we just went through, but that's not really necessary because the only difference from this to this are the two indexes. So what we can do is to copy this expression and then rename alpha to beta and beta to alpha. And that's exactly what we'll do. Okay, the final step in the parade is that we need to subtract this expression. We'll subtract this one from this one. So we'll add this, we'll subtract this, we'll change the sign of every term here and combine all this together. Now at first blush it looks like this is going to be a bloody mess because we've got 7 terms here and here. Combine them, it looks like we're going to have a result that's got 14 terms. But fortunately that's not the case because a number of these terms will cancel out. So let's look at that. First of all, this term will cancel with this one. They're both second partials, and we know the order of the differentiation doesn't matter, so these two terms are identical. This one subtracting from that one gives us 0. Well, look at this guy and this one. The only difference between these two is the order of the indexes and the Christoffel symbol. And you know that doesn't matter. We can flip A and alpha and beta here. It's the same as this. Likewise, and for the same reason, these two disappear. Okay, there's one other case. Take a look at this expression right here and this term right there. Now, they don't look identical, but they really are. The free indexes are in the same place. We have lambda, beta, and alpha in the same place. The only difference is the dummy index. So if we renamed omega to sigma here, it's the same as this. So you can always look for cases where the free indexes are the same and the dummy indexes then don't matter. Okay, for exactly the same reason, this term will cancel this one. We can rename sigma to omega, and these two are identical. So after all of that, we're left with only 4 terms, and that gives us the final expression that we're looking for. All right, so what we have is this term right here minus this term here, and this term minus this term. Notice that we have a common factor of t omega here in each term. So what we can do is to factor that out and use what's left to define the Riemann Christoffel tensor. Using this new definition, we can rewrite our result as follows. All right, well, what we're saying is if we want to know what we get when we apply this commutative operator here to a contravariant vector component, all we need to do is to form the contraction between that vector component and our new object here along this index right here. Now, just incidentally, the official name here is the Riemann Christoffel tensor, but it is most common to refer to this simply as the Riemann tensor, and I'll do that myself going forward for brevity. Okay, well, we said this thing is a tensor. How do we know that? Well, by the quotient theorem. On the left side, we took the covariant derivative of a vector, which will give us a tensor. Then we took the covariant derivative of that, which gives us another tensor. We did it in the opposite order, which will give us a tensor. And when we subtract one from the other, then we know that this is a tensor on its own. Well, of course, we know this factor is a tensor. And because of the quotient theorem, that means that the remaining factor here is definitely a tensor. Now it's going to take us several videos to fully explore the properties and applications of the Riemann tensor. But before we end this video, there's one more thing I want to do. The Riemann tensor is a fourth-ranked tensor with 1 upper index and 3 lower indexes. Well, sometimes it's appropriate and more convenient to work with this tensor in the form where all 4 of these indexes are in the lower position. So let's lower the index into this first position over here. And of course, we know how to do that. We contract each of the terms throughout the expression with the covariant metric tensor like this. And when we do it, we can lower these indexes. Now, normally this is a trivial exercise. This will lower here and here. But we have a little bit of a problem with the term right here and this term right here. It's very tempting to think that this contraction will simply lower the index here, but that's not the case. Now, if this were a covariant derivative, then it would work that way because the covariant metric tensor is metronylic, as you recall, and so it just works across the covariant derivative to raise or lower indexes. But this is a partial derivative, and it doesn't work that way, so we've got a little more work to do. So let's go over and look at this particular term by itself and see what we need to do. We'll start with this expression. Now this product right here is the equivalent of this term right here. This is just what we'd use to lower the delta index, replacing it with lambda in the lower position. So this would lead directly to that. So what we're going to do is to take the partial derivative by using the product rule here. So what we want to do is to solve for this expression. So what we'll do is switch sides of the equation and then subtract this guy from both sides. So I've swapped sides of the equation. Now I need to subtract this term. But as I do that, let's remind ourselves of what this partial derivative of our metric tensor really is. Back in video 68, we learned that this is really gamma delta lambda alpha plus gamma lambda delta alpha. So this term in the parentheses here is the equivalent of this partial derivative. So we add on this extra factor right here. Okay. So now if I distribute this term to each of these, we wind up with the final expression for this term over here. Okay, as I pointed out a few minutes ago, it's very tempting to think that this is just the equivalent of this, where this factor would pull this delta index down to make it lambda like this. So it's actually tempting to think this is all there is to it. In fact, I've seen some textbooks and videos where the authors actually did this, and it's not correct. In order to get this correct, we have to have these additional terms here as well. Okay, well now that we have this result, we can go back and make this substitution. Now we just go through our expression here and lower the index in each of the terms. Well, the first one's easy. This is just very straightforward. This is just r lambda omega alpha beta. It's just a simple contraction of these two tensors. All right, but for this particular term now, we have to make the substitution for what we derived just a moment ago. So these three terms taken together are the equivalent of this one term right here. Okay, now look at this term and compare it with this one. They're almost the same. They are the same, in fact, except that alpha and beta here are reversed and we have the negative sign. So for this term, all we need to do is to copy this one, change the sign of every term, and swap the values of alpha and beta. So these three terms taken together are the equivalent of this term. All right, all we have left then are these last two terms, and they're easy because they're simple contractions. We'll simply pull these indexes down in place right there. Okay, well, look now at this term. If I flip these two indexes, which I can do, of course, because they're symmetric, and then I rename the delta dummy index here to sigma, then this term and this term are identical with opposite signs. And that means that these two are the same and therefore will cancel each other out. Okay, well I can do the same thing with these two terms. If I flip delta and beta here and rename delta to sigma, then I get the same expression that this term and this one are going to be the same, and therefore they cancel out. So these will drop out as well. And then the only other thing I want to do is I want to rename delta to sigma here and here and here and here. So with that in mind, we now have the final expression that we're looking for. This is the definition of the Riemann tensor with all four of its indexes in the lower position. With that, we'll end the video and do a quick recap. In this video, we examined what it means to apply the commutative operator here to a contravariant vector component. We first take the covariant derivative with respect to beta, then we apply the covariant derivative with respect to alpha. We do the same two operations in the opposite order and subtract the two to get the final results. Well, along the way, I introduced an alternate form of the syntax over here. It means exactly the same thing, it's just a more concise way of expressing the relationship. Well, as we expanded all of this out, we were able to define what we call the Riemann Christoffel Tensor. Now, the initial definition is a fourth-rank tensor with one index in the upper position and three in the lower position. We then showed how to lower this upper index so that we have another definition that has all four of the indexes in the lower position. It is still, of course, a fourth rank tensor. Now we use the one that is most appropriate for the context at the time, depending on what we're doing. Alright, so with all of that, we now know that applying the commutative operator to our contravariant vector component is just a matter of forming this contraction. We form a contraction of the contravariant vector component with the Riemann tensor here along this particular index. Now we'll learn later on what it means to apply this operation to vectors where the indexes are in other positions, or perhaps tensors of higher rank. But for now, at least, we know how it works for a contravariant vector component. Well, in the next video, we're going to begin to look at some of the properties of the Riemann Christoffel tensor.